All right, in the last video what we did is we talked a little bit about how we might calculate the electric field for a line charge at some arbitrary location. What we ended up with was a situation where the resulting electric field components were both in the x and y direction. The integrals looked like they were pretty difficult to do, and so there was this, I suggested that what you should do is build them up and put them into Wolfram Alpha and solve them. What we're going to do as a real example here is to choose a location that's a little bit simpler, and we can do that work kind of all analytically in a relatively straightforward way. So the calculation that we're going to do is we're going to determine the electric field at the end of the rod, some distance b away from the end of it. And what we've done here is figure out that the contribution to the electric field due to that chunk of charge is the same as we derived in the previous video. Nothing has changed here. The only thing that's different now is that we've actually simplified our problem to be focused in on one dimension. So our hat in this case is now just x hat. It's just a one-dimensional problem. So in fact, what we have is a situation where we're only going to have to deal with calculating the x component of the electric field. So we will write that out as 1 over 4 pi epsilon naught q over L dx over r squared. Now I still left the r squared in there because we actually need to figure out what that separation vector is. So if we're looking at where the source is just along this line. It is a distance x away from the end, just like in the last video, where we say that it is an arbitrary location for the source at some distance from the end, x. Now the observation location is a distance L plus b away from the origin. It's the full length of the rod plus a little bit more. So our observation is L plus b away. And as a result, we end up with a really simple, compared to the previous video anyway, description of the separation vector r, which is always observation minus source, and it's equal to L plus b minus x, comma 0, comma 0, right? Which means that the magnitude of that, which is what we need here, and is actually just the square of this square root. So we can write down r squared actually really easily as L plus b minus x squared. So now we have cast our problem as the total electric field in the x direction, which is all of the electric field in this case because it is only along the x direction, is the integral of dEx, the sum of all the little pieces, and thus the integral 1 over 4 pi epsilon naught q over L, the integral from 0 to L, starting at this location and ending at that location, that is going along the whole length of the rod, dx over L plus b minus x squared. So this integral is all that we need to do. This integral can be done in Wolfram Alpha if you want. It can be looked up in integral tables and so forth. But it's actually kind of a straightforward one. It's just 1 over this value. So what we'll end up doing is just integrating that in any way that you like. And you'll end up with L plus b minus x evaluated at 0 and L. And so we can plug that in. It'll simplify a little bit. So we'll go ahead and just do that briefly. So 1 over 4 pi epsilon 0 q over L evaluated at the limits of L and 0. So we put an L in here. That L and that L are going to subtract. So we're going to end up with 1 over b minus, we're going to put in 0 here, 1 over L plus b. So that's our result. Now, how do we actually make sense of that? Do we make sense of it as having the right direction? Well, we have to clean this up just a little bit to be able to make that argument about how this actually will make sense. One way to do that is to put these over a common denominator and say that what we have is 1 over 4 pi epsilon 0 q over L. I'll multiply this one by L plus b, multiply this one by b to put them over a common denominator. So they're both over b times L plus b, which is a positive quantity. And so what we end up with is L on top, because L plus b minus b will give you just L. Now if you look at this, these two L's cancel, and we end up with something that's a little bit simpler, which is 1 over 4 pi epsilon naught Q times the quantity B times L plus B. If Q is positive, that is a positive value, which makes sense. The electric field should point to the right if this charge is positive. It points away from positive charge. It points away from all the added up positive charge. If Q is negative, this value is negative, and so the electric field will point to the left because it will point to the left because all the negative charges add up to give you something that points to the left. So what we've done here is a full sort of derivation of the entire electric field associated with the rod at this location, and we've made sense of the result, which is namely the direction, which is an important thing to understand when you finish your calculation. Which direction does your electric field point? Did you actually get the right result? Does the sign make sense?